Okay, hi everyone. So yeah, let me share my screen and we can get started. So today we'll be looking at Gaussian elimination. This will be the second half of chapter 1. So we just covered chapter 2. We are done with that chapter. So we introduced what are matrices, the operations that a matrix can do, like matrix addition, scalar multiplication, matrix vector multiplication, matrix multiplication. We also looked at an inverse of a matrix and how do you compute the inverse. And we also lastly we looked at elementary matrices. And now we are going to come back to chapter 1 to wrap it up. Essentially at the start of chapter 1 we looked at the geometric interpretation, like we visualized what it means to solve a system of linear equations, and when we looked at the 2 and 3 dimensional cases, we explored how lines intersect and how planes intersect. And then we also introduced elementary row operations, which help us algebraically. They give us a computational algorithm to actually solve what we want to solve. So but the elementary row operations are a bit they always work. They always give you a solution to the system of linear equation you're finding, but it's tiring to write down. So we want to find a less tedious way to do it. So if for example you're starting with 2x plus 3y, x plus 2y equal to 1 and 2. An augmented matrix, just to recap, would be, how do you derive the augmented matrix? It is, you would express the left-hand side here as a matrix vector multiplication. And then you remove the variable. So that would lead to 2, 3, 1, 2, 1, 2. And this would be called an augmented matrix for the system of linear equations that we have on the right here. And to recap the definition of a matrix is simply an array, a rectangular array of numbers. The Usually we say a matrix, the dimension is m times n, where m is the number of rows and n is the number of columns. And when you look at an augmented matrix, like the one we have over here, this component is going to be called the coefficient matrix, because we derive that from the coefficients of the variables that we have. And this part of the augmented matrix is called the constant matrix, because they come from the constants of the system of linear equations. So each row in our augmented matrix represents um one equation. So right here we have another example. Given this system of linear equations, we have 3 equations with 3 variables. So equation 1, equation 2, equation 3, and my variables will be x, y, and z. So I can write this in matrix multiplication form with my constant matrix, my coefficient matrix and my constant matrix. And that would lead to my augmented form over here. Right. So the idea is that we have the same information as the original system, and we just wanna, once we know what is x, y, and z associated, so we don't want to repeat it like 10,000 times while we are doing our elementary operations. So we just remove things that are, we store the information in a way which is easy to keep track of what's going on, and we throw away parts that we can just add on at the end, like x, y, z. So here we know that the first column is always going to be associated with the coefficients from x. The second column is going to be associated to the coefficients is derived from the coefficients on y. And the third equation is going to be, the third column is going to be derived from the coefficients on z. And we get that because of the way that matrix vector multiplication works, right? We can express this, if you remember the stuff from our second chapter when we talked about matrix vector multiplication. So when we talked about matrix vector multiplication, we get this from looking at it as a linear combination. So I can express this matrix vector multiplication as x times 1, 2, 0. Second, 1, 2, 0 plus y times 3, 7, 2 plus z times 6, 14, 5 equal to 25, 58, and 19. So yeah. All right. So yeah. Okay. So like I mentioned earlier, the rows of the augmented matrix correspond to an equation. And yeah, from there, from a system, and this is just generalizing what we did earlier on, right? Earlier on, we had three variables, three equations. I showed you my own example, which had two equations and two variables. So here we have m number of equations and x1, xn, x1 to xn. So n number of variables. So this will lead to a matrix of size m times n. Yeah, times n. So yeah. Let's look at what's happening. All right. Okay. Now we want to consider the elementary operations that we saw beforehand in the context of augmented matrix. So earlier on, we applied these operations to equations, right? And we also saw that it can be yeah, so usually we apply it to equations. Now we'll see that applying elementary operations on the equations, there's a corresponding equivalent operation that we can perform on the rows of this augmented matrix. And we are going to call that elementary row operations. And the key idea comes from the fact that the rows of the matrix, augmented matrix, correspond to equations. So whatever if we have an elementary operation on a row, because we know that equations correspond to a row in an augmented matrix, we can perform this operation on the sorry, let me write on an equation. And because an equation is associated to a row in an augmented matrix, we can also perform the same operation on the row, on the associated row, on the or equivalent, right? Because they are the same thing. Equivalent row. So we'll give this same operation that we can perform on the row the name elementary row operation. So in terms of ideas, they are exactly the same. The only difference is that elementary row operations are performed on rows, which we get from the equations, but elementary operations are performed on the equations directly. So yeah. Um, yeah, so this is telling us what I just told you, and this point is important. Changes to yeah, changes to the system of equations as a result of elementary operations is equivalent to the changes in, hang on, give me a second. Uh, all right, let me share back my screen. All right, so this is taking a while. I'm not too sure why. Okay. All right. So changes to okay, sorry, I'm back. Yeah, sorry. I'm temporarily having issues with my iPad, but let me go buy a new one and I'll uh yeah. But but yeah, back to this. Changes to a system of equations as a result of elementary operations are equivalent to changes in the augmented matrix that result from the corresponding row operation. So yeah. Um so yeah, this is what I'm saying. Whatever changes we make to a system of equations using elementary operations, those changes are equivalent to the changes in augmented matrix whenever I use the corresponding row operation. So yeah. Um the ideas of the tools are the same, they're just given different terms. If you apply them to equations, they're called elementary operations. If you apply the same idea, so when I talk about ideas, what I mean are like, when we swap equations, when we deal with systems of linear equations, the equivalent form would be swapping the rows of the augmented matrix. And if you want to multiply a constant of an equation in a system of linear equations, the equivalent concept of that would be multiplying that row in an augmented matrix. So when we want to apply these operations on the system of linear equations, we use the word elementary operations. But the same operation being used on the augmented matrix is going to be called a row operation. So the difference in terminology is to make it clear that we are doing the same operation but on a different set of objects. The first object that we deal with might be the equations, or so I guess the set of objects might be equations or the augmented matrix. But we just want to be clear what we are dealing with when we use the operation. That is why there are two different terminologies for the same word. Okay, now let's actually introduce the row operations. So the elementary row operations consist of the following. We can swap two rows. Remember, this is equivalent to swapping two equations in elementary operations. We can multiply a row by a non-zero number. This is equivalent to uh multiplying an equation in our system of linear equations. In our system of linear equation by elementary operation. Or we can replace a row by a multiple of another row added to it. The equivalent form of that would be replacing an equation with a multiple of another equation added to it. Okay? So we did this example 1.9 in one of the previous videos. We can whatever elementary operations we perform to solve that example, we can do the exact same steps, except now in the context. So the context varies in terms of an augmented matrix and using row operations. So the first step that we used then was to would be to take -2 times the first row of the augmented matrix and add it to the second row. So we want to take -2 times the first row, and I'm going to write it this way. So the first row is going to be 1, 3, and 6, and add it to the second row, which is 2, 7, 14. So that would give us -2. Maybe let me add a plus sign here. -2 plus 2, so that is 0. -2 times 3, that's -6, plus 7, that's 1. -2 times 6. I guess I meant 3. -2 times 3 plus 7, that's 1. -2 times 6 is -12 plus 14, that's 2. So we'll replace our second row with this row for the coefficient side. For the constant side, we would have -2. We would have -2 times 25 plus 58. So that would give us 8, right? So that would be on the constant side. Okay, and then we would have then yeah, so I think I pasted this down here. So that's gonna be the original example that we solved um in example 1.9. And then what we do is we um take -2 times the second row and add it to the third row. So yeah, I'm not gonna write this down, but it's essentially gonna be the same as what we did in the earlier step. And then we have this augmented matrix over here. And if I want to write it down in terms of matrix vector multiplication, it's going to be 1, 3, 6, 0, 1, 2, 0, 0, 1. And it's going to be X, Y, Z. And that's going to be equal to 25, 8, and 3. And yeah. And that will lead to, when we carry out the matrix vector multiplication, that would lead to the corresponding system of linear equations over here. Yeah, so that's how we get the corresponding system of equation. And then by back substitution, we can state that x is 1, y is 2, and z is 3, right? So yeah. So through a systematic procedure of row operations, we can simplify an augmented matrix. And we can bring it to its row echelon form or reduced row echelon form, and we'll define this next. Okay, so I've not introduced these terms yet. But before we do that, we want to introduce a term called the leading entry of an of a row. Okay, so the leading entry of a row is the first non-zero entry of a row when we look from left to right. So looking at this example I have here in row 1, when we scan from left to right, this is the first non-zero number. So this is the leading entry. In row 2, this is my first non-zero entry. So this is my leading entry for the second row, and this one right here is the leading entry of the third row because it's the first two numbers are 0, right? So there are 0 entries. So the first non-zero entry is 1. So yeah. So let's look at this definition. An augmented matrix is in row echelon form. Short form, we call it REF. If all the non-zero rows are above any rows of 0. So if I have a row that consists of entirely 0 on both the constant and the coefficient sides, I want to shift that to the bottom. I want that to be at the bottom. So looking at the example here, the matrix on the left is not in REF form because the row with all the zeros is in the middle. It's not at the bottom of the augmented matrix. But if I shift it down, then if I swap rows 2 and 3, it becomes in REF form. And the second condition is that each leading entry of the row is in the column to the right of the leading entry of any row below, any row above it. So this means that we want the leading entries to go from left to right diagonally. So yeah. So this is what it means. Because the row element is on the left, sorry, the leading entry of so because the leading entry of the row in the leading entry of the element in sorry, let me get this right. Because the leading element of the first row is on the right of the leading element of the second row, or equivalently, the leading element of the second row is on the left of the leading element of the first row. It's not on the right. The second condition is not satisfied. But if we swap the first and second rows, the leading element on the second row is on the right of the leading element of the first row. So now we can say it satisfies the second condition of the REF form. So I think the language is a bit convoluted in a way for me personally. So the way that I think about it is, as I go from top to bottom, the top row to the bottom row, the last row, the leading entries must go from left to right. So in a diagonal way, it must go from left to right. That's how I look at it, like visually. I think that's a lot easier to say. And lastly, each leading entry of the row must be equal to 1. So that's clear. Now I want to introduce the reduced row echelon form. This is almost exactly the same as the row echelon form, but it has one further condition. So all the entries in the column above and below a leading entry must be equal to 0. So in this case, in this matrix here, the leading entry of the second row, I'm gonna circle that in orange. That is 1. And the elements above and below this also needs to be, they are not 0. So I have to change this entries to a 0, the entries below and above the leading entry, and then it satisfies the condition to be a reduced row echelon form. So just to be clear, the first 3 conditions for the row echelon form and the reduced row echelon form are the same. So the reduced row echelon form just has an extra condition. Because we are adding an extra restraint for it to be a reduced row echelon form. Every reduced row echelon form is also a row echelon form, right? Every matrix, or let me say it in a grammatically right manner. So every matrix which has the form of the reduced row echelon form also satisfies the conditions needed to be a row echelon form. Therefore, it has the row echelon form. But that is not true the other way around. That is mentioned over here. Because what that means is that um we can have matrices which are in row echelon form, but they do not satisfy the fourth condition required to be in the reduced row echelon form. Okay, cool. Now let's look at examples so that they are clear. Okay. So right here I have the definition of row echelon form. And we want to show that these matrices are not in row echelon form. So they should not satisfy one of the conditions. So for the first matrix here, it's easy to see that the row of all zeros is at the top, but we need to shift it to the bottom, right? So that is why condition 1 is not satisfied. So I'm going to say condition 1 is not true. And condition 1 can be seen over here. And if this is too small, you can just go back to the definition of row echelon form. All I did was copy paste that over here. And let's look at the second matrix right here. Let's identify the leading ones of this matrix, okay? So yeah, let's look at the leading ones of this matrix. So yeah, let's look at the second matrix right here. So let's identify all the leading entries. So is recall the definition of a leading entry is going to be the first non-zero number in each row, right? So in this case, it's going to be 1, 2, and 4 for the first, second, and third row respectively. But recall the second condition that each leading entry of a row is on the each leading entry of a row is in the column to the right of the leading entries of any row above it. And this is clearly not satisfied over here, right? So yeah. So yeah, that's why it's not in reduce it's not in row echelon form. Because otherwise these two entries, the 2 and 4, has to become zeros. All right. So then let's look at the third column. The third matrix. We can see that what we want is a few conditions are not satisfied, right? Because here we can see clearly the leading entry of the first row is the second entry. So yeah, we can see that the leading entry of the first row is going to be the 2, which is the second entry, but over here we have the 1, which is towards the left of it. Because remember when I said visually, when we look at the leading entries, when we go from the top row to the bottom row, they have to go from left to right. But in this case, it's the opposite. So it's not satisfying condition 2. So again, the third matrix is not in row echelon form. Then similarly, we can look at we can work through the conditions for example 1.5. We will show that they are in row echelon form but not in reduced row echelon form. So let's look at the conditions of the row echelon form. So first of all, we need all the non-zero entries to be above any rows of 0, and that's true. We have one row of 0 over here, and that's at the bottom. And for the second bottom row, it's gonna be going from left to right. So in this case, it is 1 here. This is our second leading entry. This is the leading entry for our third row. Our fourth row does not have a leading entry because it has no non-zero terms. So since we are going from left to right, when we go from top to bottom, it satisfies that condition, and all of the leading entries are 1. So it satisfies condition 3 as well. So the first matrix is in row echelon form. It is not in reduced row echelon form because the fourth condition here, all the entries in a column above and below the leading entry need to be 0, but that's not true, right? Because for the leading entry for our second row, the entry above that is a 6. It is not a 0. And for the leading entry on our third row, there are 2 non-zero terms above it, right? So that condition is not satisfied. We can apply the same logic for our second and third matrices, and we can see that they are not in reduced row echelon form, but they are in row echelon form. And for example 1.16, the we can see that if we work through the definition, the conditions in the definition of the reduced row echelon form, we can see that they satisfy all the 4 conditions. So they are in fact in reduced row echelon form. So why is it advantageous? Why to bring a matrix to reduce row echelon form or row echelon form? And why do we even have that in the first place? That's what we are going to answer next. When we have a matrix in row echelon form or reduced row echelon form, it easily helps us identify something called the pivot position and pivot columns of the matrix. So this pivot position and pivot columns can be derived from our leading entries. So for the definition, a pivot position in a matrix is the location matrix. So trying to break it down, when looking at so the location of a leading entry gives us the pivot position, and the pivot position helps us identify the pivot column, because a column containing a pivot position is a pivot column. A column containing a pivot position is a pivot column. Yeah. Okay, cool. Let A be this augmented matrix. How do you find the pivot positions and the pivot columns of the augmented matrix A? Let's look at that. All right. So, all right. Okay. So the row echelon form of this matrix is given as such. You can deduce that on your own, because we have been through that multiple times. So now let's identify the leading entries. So the leading entries are going to be the first non-zero entries of each row, right? So now these are the pivot positions. From there, we can identify the pivot columns. So they are the columns that belong to the the pivot position. So the first column is a pivot column, and the second column is also a pivot column. The third column is not a pivot column because it does not have any pivot positions, and it does not have any pivot positions because there are no leading entries. All right, and that's straightforward. So now we have an algorithm that helps us bring a matrix to its row echelon form and reduce row echelon form. And this algorithm it always works. Okay, so the benefit so it's like procedure, right? It's the stuff that you do to help you get your matrix to its reduced row echelon form. And remember, every reduced row echelon form is also a row echelon form. So this helps you get your row echelon form too. So for the first step, what we want to do is we always want to start from the left, and we first find the first non-zero column. So sometimes you have matrices where everything is zero in column wise, and you want to ignore that. So what we want to do is and this yeah, so yeah, once you find the first non-zero column, this is the first pivot column, and the position at the top of this column is the first pivot position. So what we want to do is, once we identify this first pivot position, we want to swap the rows if necessary and place the non-zero number in the first pivot position. And then what we want to do is we want to use row operations. If this seems too abstract at the start, don't worry, we are going to go through a bunch of examples to make it clear. But I just want to give an overall picture of how the algorithm works. But after a while, as you get used to it, it's going to be intuitive. Like you can like go with the flow and just do it. We will not be looking at the um algorithm and following it like step by step methodologically, because it is kind of intuitive. Like later you'll see. Um Then we use the row operations to make the entries below the first pivot position equal to 0. And then ignoring the row that contains the first pivot position, we are going to do step 1 and 2 for the remaining rows. So what we are going to do is we are going to do step 1 and 2 for the first row, ignore the first row, do it for the second to the last, redo step 1 and 2 for the positions for the second to the last row. And once we complete steps 1 and 2 for the second row, we ignore rows 1 and 2 and we go to the third row. So we're going to repeat this process until there are no more rows to modify. And then lastly, we'll divide each non-zero row by the value of the leading entry so that the leading entry becomes 1. So now it's in row echelon form at the end of step 4. And moving from right to left, we use row operations to create zeros in the entries of the pivot column above the pivot positions. So yeah, we do not have to deal with the case below the pivot position because that's dealt with in step 2. And now the matrix will be in reduced row echelon form. So let me just let's go through a bunch of examples, and then it'll seem clear. All right, cool. Find the row echelon form of A. And then we want to complete the process until it's in the RREF form. So we are going to do the steps outlined in algorithm 1.19, which was just above. So the first pivot column is the first column of the matrix, right? Because the first column of the matrix itself, it's non-zero, right? From the left. Like we do not have a matrix which is 0, 0, 0, and then something else. So yeah, the first column itself is a non-zero column. The first pivot positions are the ones in the so we want the first pivot position to be at the top. Essentially, that's what the second line says. But now it's a 0, right? And pivot positions are leading entries, so they have to be non-zero. So what we are going to do is we are going to swap the first 2 rows to obtain a non-zero entry in the first pivot position. So we swap rows 1 and rows 2. This is our first row operation. And then our first pivot position goes to the top, right? Okay, cool. And then step 2 of the algorithm involves creating zeros below the first pivot position. So this is our first pivot position. At the top, I want to make the entries below the 1 in the same column 0. So the second entry is already 0. So I need to just make the 5 0. So all I need to do is subtract 5 times the first row from the third row. And this is the resulting matrix. So this is the third operation in our elementary row operation, in our elementary operations, right? Or we can call it elementary row operations, because we are doing this in rows for the object rows, right? And now what we are going to do is we completed step 1 and 2. So we'll ignore the first row and then the first column as a result, and we'll take this smaller square matrix and then we'll apply it to the smaller matrix. We'll redo steps 1 and 2 to the smaller matrix. So in the smaller matrix, the first column is the pivot column because it's non-zero. And this is going to be my pivot position. And I want it to be, I want everything below that to be 0, right? Sorry. This is my pivot column, and the -5 is my pivot position. So I want everything below it to become 0. So I want to turn the -10 to a 0. So all I need to do is add -2 times the first row to the second row. This will be the resulting matrix. And now I can plug this back into the original matrix. I'll replace this smaller 2 by 2 matrix that I started with. So this, hang on, I'm not able to. Yeah, give me a second. So this smaller 2 by 2 matrix, the -5, -10, -4, -8. So yeah, that one. And now we can see that they are okay, let me stop share and share back to remove the, yeah. So now we need to create leading, yeah. So now the original entry looks like this, entry to be 1. So the first leading entry is a 1. The second leading entry is a -5. So the third row does not have a leading entry, so we do not need to be concerned about the third row. So no work needs to be done for the first row, but for the second row, I need to make the -5 into a 1. So what I do is I multiply the entire row with the constant yeah, I divide it by -5, right? And that converts the -5 into a 1. So this is my second operation in my elementary row operations. So yeah. Now we have our matrix in row echelon form. We need to make it into a reduced row echelon form. So I need, for the first leading entry, the entries below that are both 0. For the second leading entry, the elements below it are 0 because the second step in our algorithm takes care of it. But the 4 at the top, we need to make it into a 0. So what I do is I subtract 4 times the second row from the first row, and that results in my reduced row echelon form. So yeah. So the idea is pretty simple. It gives you a simple way to a simple systematic way. And the reason why it is good to follow this is you do not confuse yourself, right? You go, it's method, yeah, it's systematic. You go from one matrix to a smaller matrix, and you break down the matrix into smaller sizes, and you add them back up together. If you do it in your own way, it might work, but sometimes you tend to confuse yourself and you don't know where you're going, right? So the main idea is to do row operations in such a way that you end up with a matrix in REF or RREF. And this process is important because it allows you to get the solutions, or to describe the solutions to the corresponding linear equations in a meaningful way. So let's try to solve this system of linear equations using what we have learned, right? Okay, so we give the complete we want to give the complete solution to this system of linear equations. We can write this down in this augmented matrix form. In order to find the solution for this particular example, we want to bring the matrix, the augmented matrix, to its reduced row echelon form. So we are going to use the algorithm which we first learned. And so the first column right here, 2, 5, 3, is non-zero. So it's going to be our first pivot column. So the first entry, the topmost entry, is going to be my pivot position. So this is going to be my leading entry, right? All right. So what we want to do is we want to use row operations to make my 5 and 3 into zeros. So first I'll replace the second row with -5 times the first row plus 2 times the second row. That would change my second row to this. And then what I want to do is I want to replace my third row with -3 times the first row plus these 2 times the second row. So this would become this. So now we can see that every entry below the leading entry 2 is 0. All right, okay. So now we look for the second pivot column. In this case, my leading entry for my second row is in the third column, right? It's not in the second column. So my third column is going to be my pivot column. Oops, sorry about that. Yeah, my third column is going to be my pivot column, and yeah. Uh, Let me just clear my screen and then I'll be right on it. Okay. Um, yeah. So now all we need to do is just make the entry below the below this one 0. So I want to make this one equal to 0. So what I'm going to do is I'm going to take -1 times the second row and add it to the third row, and then it yields something like this. We can carry on further, but something that we want to take note of is the third row of the matrix, right? So what does this mean when we look at we know each row corresponds to an equation, right? So what does this mean when we look at the equation? This tells us that 0 times x plus 0 times y plus 0 times z is 20. And the reason for that is when we go way back, when we introduced the augmented form, we said that the first column contains coefficients of x in each equation. The second column contains coefficients on y in each equation. And the third column comes from the coefficients of z from each column, right? So I'm going to apply that knowledge to, yeah. Here, this particular row over here, and then that gives me this particular equation. And this has no solution, right? Because all of x, y, z times y plus 0 times z is just 0. And then the right hand side is 20. But this tells us that 0 is equal to 20. And this does not make sense, right? So this shows that there's no solution to the system of given equation, because no matter what x, y, and z is, you're never going to satisfy 0 equal to 20, because that's mathematically invalid, right? So this tells us that this system is inconsistent. So there's no solution. So this example right here is an example where we have an infinite set of solutions. So I'm going to skip the part where they are applying the row operations to get the reduced row echelon form, because we have gone through the elementary row operations a lot of times, and what we looked at, the algorithm, is just a systematic way. They just tell you the order, or yeah, the order to perform the elementary row operations using the positions of the augmented matrix. There's not a lot of new things to it. They just tell you this is the order that you do it in. So yeah, I'm going to skip those steps because I've done it a lot of times. But I think the key thing is to go to the reduced row echelon form, which we can verify using the definition, right? Because the leading entries are now 1. They go from left to right. Everything below and above the leading entries are 0. And all the 0 rows are at the bottom. So all 4 conditions of the reduced row echelon form are satisfied. And when we look at the reduced row echelon form and we bring it back to the equation form, so let me write that down, because this is equivalent to 1 0 negative 5 0 1 10 0 0 0 times x y z 3 0 0, and then carrying out our matrix multiplication, we have x minus 5 z equal to 3, y plus 10 z equal to 0. Then this is all 0 and this is 0. So 0 times x plus 0 times y plus 0 times z is equal to 0. That gives us all zeros, right? So that gives us all zeros. So yeah, now what we want to observe is t is not constrained by any equation. Z is not constrained by any equation. Like when we make x and y the subject, what we have is x equal to 3 plus 5z, y equal to 10z. But our system of linear equation does not tell us that z has to be something. So what does that mean? I can in fact let z be any number. Like it can be any real number. It can be 5, negative 16, 1,000, negative 3 over 17. It can be any number because we are not constrained by any equation. So in this context, I can let z be t, where t is any number. And in this context, what we state is t is a parameter. Okay, so we state that t is a parameter, and therefore we can. And what we are going to state is that t is going to be any t is. So this is good to write down in your exam or whatever. Whenever you have things, okay, let me write it down. And I'm having issues with my iPad. I'm thought I resolved it, but somehow it's acting up again. I'm not exactly sure why, but yeah. Let me waiting for my iPad to reconnect. It keeps disconnecting, and I only have this issue when I'm recording my screen. I'm not exactly sure why, but yeah. Let me yeah, so let me write it down. So t is any real number. So this is an important statement. Or you can say t is in the set of real numbers. So 1 or 2. And once we state this, we can let z be equal to t, which is any real number. And because z is t, I perform the substitutions t here and t here. and that would give us our infinite set of solution, because t can be any number. So for each number t, I would have a solution, right? So because z can be z has an infinite possibilities, and for each of these possibilities, I can substitute that possibility and get an xyz, which is the solution. I have an infinite number of solutions. For example, if we chose t to be 4, then the corresponding equation would be, the solution would be x equal to 23, y equal to 40, and z equal to 4. So yeah. Then we can also have more than one parameter, and you can you can refer to this example that shows you that. So essentially, when there's no constraint, so something like when we deal with in this case, right, we have let me write it down. Okay, so we have x plus 2y minus s minus, sorry, z. Yeah, we have x plus 2y minus z plus w equal to 3. We have y is equal to 2. That's our second equation. Y is equal to 2. But there's no, so when I make x the subject here, x is equal to 3 minus 2y plus z minus w. Since y is 2, I can write it as x equal to -1 plus z minus w. So I have y is equal to 2. There's nothing, after I get my reduced row echelon form, there's nothing about my z and w, right? So we can assign parameters to z and w. So we'll assign parameter s to z and parameter t to w. Something I want you to take note of is the subjects of my two equations here, they come from my pivot positions. My parameters come, so the first column corresponds to x, the second column corresponds to y, the third column corresponds to z, and the fourth column corresponds to w. So my two pivot positions, pivot columns, gives me my subjects of the final equations, and the parameters, we can see that they come from my non-pivot columns. So pivot columns have they become the subject of my equations, subjects of equations. But non-pivot columns become my free parameters. My parameters, or my parameters. So I have to introduce variables for them. So here s and t are going to be my real numbers, or you can say s and t are real numbers written down in words. So yeah, once I let s and t be real numbers, what I can do is I can just let z be s, w be t, and I can perform the corresponding substitutions into x. So yeah, let's see what's written over here. So over here, what they're stating is that you can also bring it to you can also, we stopped at the row echelon form in our previous example, but we can also bring it to our reduced row echelon form, and they would give you the same answer. So you have two paths. You can use the reduced row echelon form, or you can use the row echelon form, but it must be one of this. But they both lead to the correct answer. So either approach can be used. If you use the first approach in the above solution, so if you go to the row echelon form and then try to compute the solution, is the Gaussian elimination. So what we do is in Gaussian elimination, we carry the matrix to the row echelon form, we convert it back to equations, and then using back substitution, we find the solution. And or what you can do is you can bring it to the reduced row echelon form. And then that would be called the Gauss-Jordan elimination. So they're both equivalent. They give you the same answer, so you can do whatever you prefer. So there's still one page left in this chapter, but this video has been pretty long, so I think I'll continue. For my next video, I'll wrap up this chapter by covering this page and this subsection, and then we'll be done with chapter 2 as well, or chapter 1 as well. So yeah, if you have any equations, anything that you need to clarify, let me know. And once again, for office hours, if you need to meet me, we can meet through Zoom, and you can just send me an email to set up an appointment. So yeah. All right.